All right, so we're going to see, we're going to do the first topic of this review, which is called Intro to Basic Complex Calculus. There are notes on this. This is not examinable material. It's things that you need to remember, recall, things that kind of you know from previous courses. But there are notes that I created, block 0. We're going to cover page 1, 2, and 3 of block 0. And, the rest of the material, there are 8 pages in that block. But the rest of the material is actually for those of you that are like me and geek out with these things, and after me telling you these things are like, oh my god, I want to know more and I want to understand. I'm gonna give you I'm gonna end this section with some like apparent paradoxes with equations, and that kind of hopefully will keep your interest in trying to learn more math. We'll see, but it's not necessary at all. It's necessary to review these things, so we're gonna do 3 pages of notes now and review them. And the bonus that you get from, this is things that you know, but the bonus that you get out of watching this, when you unlock the achievement, watch the introduction to complex calculus video, is I'm going to end with a trick that once you know and you use it for complex calculus, you know how horrible it is to try to remember the multiple angle formulas. Oh, the double angle formula, what was it? What about the triple angle formula? I don't remember. I never remember. I always derive them. And you can derive them with one line, or almost one line, with a trick of complex calculus. So that's gonna be my gift to you. If you don't know it yet, I'm gonna show you how to never have to remember or to write down multiple angle formulas. You can derive them like this fast, okay? Like this fast. Sorry about that, guys. All right, so let's begin the course. All right, so what is a complex number? Well, a complex number, you may know, is we actually say a complex number set, which is an element of the set of complex numbers, is a number that can be represented as z is equal a plus ib, where a and b are real numbers, and this I, the imaginary unit, satisfies that the square of it is -1. Notice that I am using I and not j. Everybody uses I except for some engineers. And I know electrical engineers are kind of like super big on not using I. I'm sorry, guys. I'm a theoretical physicist, and even physicists that work in electronics, they still use I most of the time. Yeah, that's what the world is. So it's good in the sense that you get exposed to different conventions and you exercise the muscles of your brain. Think of it as a workout, the fact that I'm going to be using I. For me, I feel that I'm violating some sort of fundamental principle of the laws of physics. If I were to write a J here, it would not work. I will forget, I will write I, so let's just be consistent and write an I, shall we? Hopefully, we can chat about these things in the in-person sessions that we have. Well, in person, you know what I mean, online. All right, so let's review a little bit things that you already know. So if I give you a complex number, for a complex number, let's say z equals a plus ib, right? We define the real part of z, that we annotate real of z, well, this is just a. And of course, this is a real number. The imaginary part of z that we notate as imaginary of z, this is b, and it's of course another real number, the imaginary part. Now we define the conjugate of z, which we call z star, and we define it as, this symbol means definition. Don't confuse the symbol definition with equivalent, which is 3 bars. 3 bars is not a definition, it means equivalent. This is a definition. So we define the conjugate as the same real part, change the sign of the imaginary part. And finally, we get the modulus of z, and the modulus of z is the positive square root of the product of z times its conjugate. Now, of course, this modulus of z, that we notate like that, z squared, let's write it, is z times z star right? And then of course that means that this is A plus IB times A minus IB. Okay? If we expand this product, we get A squared, then we get minus IB squared, right? And then we also get plus IBA minus IBA, that cancels, so that's all that is left. And if we undo this, if we have to do this square, we get the I squared is minus 1, so we get that this is A squared plus B squared, okay? So the modulus of Z squared is A squared plus B squared, and the modulus, as I said, is the positive square root of that A squared plus B squared. All right, you knew that. Now, we can represent graphically the complex number Z, and I'm gonna go MIT level. So what makes MIT professors so good? The fact that they use multiple colors and nothing else. Well, so MIT of the North level here. So we have the complex number Z, and now this complex number Z, right? We have two axes, right? This axis, the x-axis here represents the real part of Z. The y-axis represents the imaginary part of Z. Okay? So therefore, we have the projection here on the x-axis is A. This thing here is A, the real part. This projection here is B, the imaginary part. All right? And then the length of it, this amount of length is the modulus of Z, right? Of course, you see it's the hypotenuse of this rectangular triangle, where you know B squared plus A squared is modulus of Z squared, right? Which is what we derived. All right, so we can introduce another little concept here. We can introduce the angle phi that it forms with the x-axis. So this angle phi is what we're going to call the argument of the complex number. So phi is the argument of Z. Okay? And it's going to play a role in the next thing I'm going to tell you. All right, so any questions so far? Of course, you cannot ask them right now live, but what I'm inviting you to do is to pause the video, think about the questions, and then ask me in the live sessions. We can actually draw here the conjugate of Z as an exercise. Let me do the conjugate of Z in black. So if I do the conjugate of Z, is this number here. So this is Z conjugate with the same, you see, A is the same, the real part is the same, but now the imaginary part, right, is changing sign. So it's a length B, but in the negative imaginary part. And of course they have the same length, so the modulus of Z and its conjugate is the same. All right. Let's talk about the exponential representation of complex numbers. I'm going to erase this. Actually, what I will do is, with the magic, from the magic of editing videos, I'll do, all right. So, what is an exponential function? So, you're familiar with e to the something as being the exponential function. But what is really the core of what we call an exponential function? The exponential function, the definition of an exponential function that I'm going to give you, is the only function that we're going to call x of Z that satisfies that it is proportional to its own derivative Remember that? The derivative of e to the x is e to the x. Is the most difficult function to differentiate or integrate, right? Proportional to its own derivative, and also, and that the exponential of 0 is 1. Let me erase this and write this condition in a math equation. And we get this same thing. I'm going to say that the exponential, the derivative of the exponential of az dz has to be equal to a exponential of az. This is the property. And of course, exponential of 0 has to be 1. This is what defines the exponential function. And of course, it should ring a bell, because the derivative of the exponential is the exponential, right? The derivative of the exponential of ax should be a exponential ax. Now, with this definition of exponential function, let me propose to you. Now, right now, you know how to do exponentials of real numbers. I'm going to extend that to exponentials of imaginary numbers now. So how do I do the exponential of I times a real number? So let me define. I'm going to define for you. Let me define I to the x, e to the ix as the cosine of x plus I, the sine of x. And that's a definition. And then you may ask, why? Are you crazy or what? You cannot just define like that, can't I? Let's see if we can. So let's check if this is a valid exponential. If this function is a valid exponential, it has to satisfy this property over here. Now, that the exponential of 0 is 1, it's very easy. When x is equal to 0, cosine of 0 is 1, and sine of 0 is 0. So it satisfies that the exponential of e to the I0, which is the exponential of 0, is 1. Let's see if it satisfies the other property for an exponential. So, we need to, if the property is true, this should be e to the ix with respect to x would have to be equal to I e to the ix. Well, let's see if it's true. Let's do it. Now, the derivative of e to the ix with respect to x, it's equal with the right hand side, derivative of the cosine with respect to x plus I, derivative of the sine with respect to x. All right. But the derivative of the cosine, we know what it is the minus sine, right? And then plus I, derivative of the sine is the cosine of x. Okay? All right. So, what I can do, I can multiply by I and divide by I. So if I do that, I divide by I and then multiply by I inside, and I get the second term I'm going to put first, I times I minus 1, so cosine of x minus I sine of x. But now realize of something super cool. What is 1 over I? 1 over I, it's equal to, well, I can multiply by I, numerator and denominator, and I would get I over I squared. I squared is minus 1, so it's minus I. The inverse of I is minus I, obviously, right? Minus I times I is 1. So minus I is the inverse of I. Very cool. So this thing is actually equal to minus I, this thing, let's just put it like this, the minus I take out, and that would be I, right? The minus here is minus 1 over I, cosine of x plus I sine of x. And there we go, we got it. This is the exponential back. This thing is our definition of the exponential of ix. So certainly this thing is I to the ix, and this definition of exponential function satisfies what we want from an exponential. How is that? All right. So, cool. We have proven then that this definition for the exponential function of an imaginary number is a valid definition for the exponential. Now, because we know exponential functions of real numbers and we know exponential functions of imaginary numbers, we can do the exponential function of a complex number, which is the exponential of a plus ib. We can do this as the exponential of a times the exponential of ib, right? And this exponential of ib, that's the same. Look at this, we have e to the a, and this is cosine of b minus I sine of b. All right, so we know how to do exponentials now. Wonderful. Now, interesting fact. I'm going to erase this. Given that the exponential has this definition, one thing that we can do the exponential of an imaginary number is realize of the following. I'm going to write this e to the ix, and here the conjugate, right? If I conjugate, I get a minus here, I get a minus here, so the conjugate is e to the minus ix. So this is equal to the cosine of x plus I sine of x. This is equal to the cosine of x minus I sine of x. I can add them up. If I add them up, I get here e to the ix plus e to the minus ix. It's equal to the signs cancel, and what I get is twice the cosine of x, which means that the cosine of x, what it actually truly is, when you look at the cosine of x, is e to the ix plus e to the minus ix divided by 2. Oh, look at that. The cosine really is the sum of two complex exponentials like that. That is kind of nice because that tells you what the cosine does when nobody looks. Why? Because now I can express, you see, this is the cosine of a real number. But if I want, I can put imaginary numbers here. Now, this I know how to do this exponential, whether the x is real or imaginary, I know how to do it. So, when you look, so the cosine, that is a function that behaves really well on the real, in the real line, is just oscillating and nice. If you look behind it in the complex plane, it's an exponential. It would be the exponential of ix, right? If x is imaginary, imagine. This thing is the exponential of x and suddenly grows like an exponential, misbehaves. Again, this is a little bit beyond what I want you to learn. But just so you know, now we can understand the cosine in terms of exponentials. The cosines are exponentials when the argument of the exponentials is purely imaginary. Anyway, we can do the same thing with the difference. We can subtract now. E to the ix, e to the minus ix equals cosine of x plus I sine of x. This one, oh, my handwriting is acting up again, sorry about that. Cosine of x minus I sine of x. Instead of adding up, I can subtract them. So the cosines cancel in this case. So I get here e to the ix minus e to the minus ix, and this is equal, I'm subtracting, twice I sine of x, which means that the sine of x is actually equal to e to the ix minus e to the minus ix divided by 2I. All right, gives you more perspective. So you see, complex exponential are but trigonometric functions. Trigonometric functions and complex exponentials, or exponential of imaginary numbers, are two manifestations of the same thing. Things that oscillate. So this thing is a thing that oscillates as a function of x. Any questions? Probably. Watch this again carefully. Bring all the questions to the in-person sessions. All right. So now that we've seen this, we are prepared to write what we call the polar form of the complex number, or the exponential form of the complex number. And we're gonna demystify one of the things that you hear a lot about, the magic of math and the most beautiful relationship in math. We're gonna demystify that thing. Because oftentimes in popular culture, you get people to go crazy on, oh, look at that, e to the I pi is minus 1. E, I, pi combined, ooh. But that's nothing really. I mean, we will see what it is. It's not the magic of numbers. It's a no drama expression, and we will see what it is in a second. Alrighty, let me erase. So we can call this section the banking e to the I pi, the banking magic behind e to the I pi equals minus 1. All right. All right, so we can write, the exponential form of a complex number. What is this exponential form? Well, a complex number set, all right, it's equal to the modulus of set e to the I phi, or maybe I'll call it theta here. Easier to write. All right, so that means that any complex number I can express it as, well, this is of course the same as set cosine theta plus I sine theta, as we saw from this expression. Well, this is not surprising. This is freaking trigonometry. Remember the plot that we had before, right? Let's do it again. The complex number z, right? We have here the modulus, right? And what is the length of, remember, that was the real part. So this is, let me just write it here. This is the real of z. This is the imaginary of z, right? And it's, right, you say, okay, this is a, remember, right? This was a, but a, of course, in trigonometry is just z cosine theta, where theta is this angle, right? And the same goes for b here. This is b, but b is, of course, z sine theta, right? It's just trigonometry. And of course, this is it. So the z cosine theta is the real part, there's no i's. Z sine theta with an I is the imaginary part. And of course, this is what we define as the exponential of I theta. So it's all consistent with what we saw. Now, of course, we can write this expression. It's kind of nice because that allows us to write complex numbers really easily. So let's do a couple of examples. So if I have, say, the complex number 1. This is 1. Okay, 1 is, well, is the modulus of 1. Let's say I'm going to write complex numbers of modulus 1. The modulus of 1 is 1. So that's easy, I don't even write it. So this is the exponential of I theta. What is theta for 1? Just 0. The angle is 0. Oops. So it's I 0. So it's e to the 0. So of course, this is 1. Makes sense. Let's do the number I. This is the number I in the complex plane. So I, it's equal, modulus of I is also 1. So it's e to the I theta. What is theta? So in this case, theta is pi over 2, right? So it's to the I pi over 2. So nice. I is, oh, by the way, 1 is also e to the I 2 pi. You see, these are trigonometric functions that are 2 pi periodic. So I can write 4 pi and 6 pi. So it's modulo, you can add always, it's mod 2 pi, okay, all these expressions. So 1 is e to the 0, which is 1 of course, but it's also e to the I 2 pi, because you can do the full term. All right, let's do another one. Let's do minus I. Minus I. So we can take the angle different ways. We can take the angle to be 3 pi over 2, for example, for this one. Let's do this one. This is 3 pi over 2, the angle. So minus I is equal to e to the minus 3 minus I 3 pi over 2. Also, we could have counted this way, right? So, oh, why did I write a minus? Sorry, my bad. Is minus I is e to the I 3 pi over 2, or we could have counted pi over 2 the other way. So this is the same as e to the minus I pi over 2. Again, if you add 2 pi, you get one or the other. All right. Okay. Another one. Minus 1. So this one, the number minus 1. So what is the angle for minus 1? For the minus 1, the angle is pi. So I know that minus 1 is equal to e to the I pi. Oh my god, the freaking relation. So you see, this is not some magic or whatever, it's just basic trigonometry. We are representing complex numbers trigonometrically. We're using triangles, and then what we get out of that is this relation. I'm not saying it's not nice, this is not magic. It's not, there's nothing super dark or the mysteries of mathematics and number theory. No. This is super simple mathematics, as you can tell. So if you see somebody trying to get mystical with this, you tell them, dude, what are you talking about? No, so stop them right there. Okay, don't let them bullshit you with that. This is gonna be recorded. I probably should try not to say things like bullshit, but well, it's okay. All right, cool. So we know now how to represent complex numbers in terms of exponentials. This is kind of the end of the things I wanted to review. Let me tell you about the Moivre formulas. So the Moivre formulas is what I promise you. It will be the reward for bearing with me. You will never ever have to remember the double angle formula, the triple angle formula, etc. So let me show you. So I'm going to erase the board using the magic of video editing. Okay, so we have this expression for the exponential of a purely imaginary number. Let's do the following. Let me compute e to the I theta square. Now, of course, I can do the square on both sides, right? And then I say, on the left-hand side. Well, on the left-hand side, I know what it is. So on the left-hand side, this thing is just e to the I 2 theta. In this case, it works to multiply the exponent when it's a purely imaginary one. So, what about the right-hand side? Well, the right-hand side is a binomial, so I can expand the binomial. So that's an easy one, because what I get expanding the binomial is the cosine square of theta minus the sine square of theta plus twice I cosine theta sine theta. Right, but that thing, I can use this formula again on the left-hand side now. And on the left-hand side, I get, right, this is the same as, this is equal to the cosine of 2 theta plus I sine of 2 theta. And of course, let me just write the same thing again. Cosine square, I'm just repeating, I'm doing slowly, just for reference. Plus, but of course, this is one step. Cosine theta sine theta. And look at that, I have an equation now on the left-hand side and the right-hand side. For that to be equal, the real part of the left-hand side has to be equal to the real part of the right-hand side, and the imaginary part of the left-hand side has to be equal to the imaginary part of the left-hand side. If I write these two equations, the real and the imaginary separate, I get that the cosine of 2 theta, let's use colors. The real part on both sides has to be equal cosine square of theta minus sine square of theta, and the imaginary part, which is this, and here is this, the imaginary part also has to be equal. So I get that the sine of 2 theta is equal to twice cosine theta sine theta. And there you go, the double angle formulas. And again, I'm doing super slowly, but this is one step. You never have to remember anything. You just expand this thing. You can do exactly the same thing with the triple angle formulas, and I'll leave you, I can do e to the I theta cube equals cosine theta plus I sine theta cube, and I can do here e to the I 3 theta, and here I expand there, it's a cube, right? So a couple more operations, but no worries on the notes, it's just 3 terms, And again, and you get, the expansion of this, you do it, and you get the triple angle formulas, which is, I'll write them here. You also get that the cosine of 3 theta is equal to cosine cube of theta minus 3 times cosine theta sine square theta. And also get that the sine of 3 theta is equal to 3 cosine, 3 cosine square theta sine theta minus sine cube theta. And that works for all the powers. It's just expanding and very simple steps. And this is actually called I'm gonna write the title. So you see, I'm losing the MIT bonus. I'm getting more to the MIT of the North in that sense. So these are called the Moivre formulas. All right, because it was the first person who did it. Super simple. Now, you will never have to remember multiple angle formulas. They're deducible in one step, like that, okay? So, you're welcome. I was really happy when I was first told for the first time about this and showed this, okay? All right. Any multiple angle formula. Now, to end, this is all that I wanted to review for you, that you remember your complex numbers and so on. I want to tell you perhaps one more thing. If you want 2 more things, I want to tell you, there's a lot more of notes about this. There are 4 more pages. That's for those of you who are really geeky like me about it and want to learn more. Let me leave you with some apparent contradictions that to understand. I related with something called in complex calculus branch cuts. Branch cuts. So the branch cuts make some things that appear to be like funny. Do you know these mathematic games where you have something equal to something and you end up with 1 equals 2 and things like that? There are several of those that you can use complex calculus. If you use it wrong, you get them. You get these contradictions. So let's see them just as a pastime. Of course, these contradictions are solved in the notes. You have to read the whole notes to get this. I will not tell you how you solve these paradoxes until, I don't need to erase that magic. So, all right, so let's see some mathematical fallacies that originate in bad complex analysis, okay? So let's start with this one. Let's begin with a simple trigonometric identity. The cosine square of x equals 1 minus sine square of x. You know that formula. I'm going to start doing steps and I'm going to get a contradiction. So one of the steps was wrong. You need to find which one and why. Okay, we can take the square roots. If we take the square roots, we get cosine of x equals root of 1 minus sine square of x. These complex numbers, so the square roots are well defined and so on. They're actually defined in the notes how to do square roots and so on. So everything is fine. You can take square roots. We can now add 1 to both sides of the equality. So 1 plus cosine of x equals to 1 plus root of 1 minus sine square of x. Okay? And now let's evaluate this identity for x equals pi. Now, of course, I know that in that case, cosine of pi is equal to minus 1, and sine of pi is equal to 0. So if I evaluate, I get 1 plus, I'll do it in the next time. I open a wormhole, and the exit of the wormhole here, okay? So I evaluate this and I say, okay, 1 plus minus 1, which is the cosine of pi, equals 1 plus root of 1 minus 0, which is the sine of pi. So what I get here, 1 minus 1 is 0, and 1 plus 1 is 2. What? Contradiction. So I've done something wrong somewhere, some step that I'm not allowed to take. What is it? Well, if you want to know exactly what is it, complex calculus, the rest of the pages in the notes. Let's do another. Okay, this is the first fallacy. Let's do another. That was one. Let's do another, number 2. Let's do this. I take 1 equals to the positive square root of 1. That is correct, no? If I take the positive square root, that is no problem with that. But now 1, I can write 1 equals this thing, I can write 1 is, of course, minus 1 minus 1. Multiply, that is 1. But I know that the square root factorizes, no? This is the square root, maybe I'll write the arrow to have the two sides. 1 equals square root of minus 1 times square root of minus 1, no? You've been doing that all the time. But this is I, so this thing is 1 equals to I times I. What? Oh my god, what? That's not right, there's something wrong. As in, like, maybe I kind of said, maybe that? I don't know. Why can't you do that? I don't know. Well, I do, but if you want to know and you don't know, please check the notes. This is trying to get you hooked with this. Cliffhangers. I'll give you a third one. I do e to the I through pi. Remember, that was 1. That was an exponential representation of 1. You take one term and you start in 1. If you're here, this is 1. You take 2 pi, you are again at 1. So e to the I through pi is 1. We just saw that. Now, I'm going to exponentiate to I on both sides. E to the I 2 pi to the I. Then, and this is 1 to the I. I just exponentiated to I on both sides, doing the same on both sides. Now, if I use the properties of the product, I know, by the way, 1 to the I is also 1. 1 to any power is I. To understand what it means to take a complex power, you actually need to also check the notes. Let me tell you something interesting before we continue with this fallacy. When you're little kids, they tell you, what is a power? Oh, it's easy. If you have a number like 9 to the power of 3, it means 9 times 9 times 9 3 times, right? 3 times. So if I say 9 to the n, it means n times, right? Right. But then soon you say, no, but I've seen 9 to the minus 3. What does it mean to multiply things minus 3 times? And they go, oh, no. What that means is 1 over 9 times 1 over 9, 1 over 9, 3 times, right? And you say, fine. But then they tell you, oh, but you can have 9 to the 1/2. What does it mean to have 1/2 there? Oh, you say, no, that's kind of a square root, so this is actually square root of 9. Well, just imagine 9 to the I. What does that mean? Oh, it's easy, right? Just 9 multiplied I times by itself. So no, they're intuitive. That kind of illustrates really well how in school you start learning, they tell you things that are not true. This is not what a power is. This is so not what a power is. The same way the exponential has this definition that I gave you, getting to the core and understanding the math of the things that are behind these definitions. What really is a power? What do powers have in common? You need to check the notes to see what is a complex power. You don't need to, for the course it's not needed. But if you're interested, certainly the notes are there if you want to check. And again, 1 to the I is actually 1, so that is correct. You can trust me on that. And then I say, oh, I use the property of the exponential. It's multiplying the exponents. So I get e to the I 2 pi times I. But I times I is minus 1, so what I would get, so again, put a question mark there. And a question mark here. Then, right, that means that on the one hand I have e to the minus 2 pi equals 1. What? This is not 1. What are you talking about? This is actually like, the way to express how surprised you should be when you say it is you add this, right? Makes it even more. It's like the perfect question if you want. Anyway, so that's it. I leave you with these 3 fallacies. If you want to learn why you can't do things like that sometimes, or things like that sometimes, and what's going on with this trigonometric relation, you need to go through the rest of the notes. No need though for the course. With the course, it's enough to go through the 4 pages that I cover, actually 3 pages that I cover in this mini intro. And that's the end of this lecture.